right, you're all set.
Thank you very much, Brendan. Thank you, everyone, for this good time, for all the participants that have been around for the summer school. And I hope many other people will take advantage of these videos and just watch at home. So anyway, thank you, everyone, and thanks to all the instructors that have done an awesome job, CTNT, and for putting this together in short notice to be online. So thanks, everyone. All right. So I'm going to continue doing some examples of things in Magma, and I'm going to move right away to my Magma screen. You can see that, correct, Brendan?
Yes.
Very good. So I promised yesterday, Zomia, during her lecture on curves over finite fields, she was working with zeta functions. So I thought I would start today with some zeta functions myself. So here is a curve we were working with last time. Is the curve x cubed plus y cubed minus 2, but in over the field of 37 elements and in projective space. All right, so there you go. So now we're going to define the zeta function. And once the zeta function is defined, I can look at it. So here is the zeta function for my curve over the field of 37 elements. You can change the field of definition, of course, and then the zeta function will change it slightly. So here is the function over the field of 13 elements. Let's see it. That's just the definition of the curve over the field of 13 elements, and now is the zeta function over the field of for the curve, which is a genus 1 curve we saw last time, over a field of 13 elements. All right, so we can try to verify that the Riemann hypothesis holds. So out of the Weil conjectures, we know that the Riemann hypothesis holds for a curve over a finite field. So let's see what happens. So I'm going to define the polynomial ring over the integers. And I'm going to look at the denominator of the zeta function. So you see that I coerced my denominator. The zeta function is a rational function, so it wouldn't know anything about polynomial rings. So I have to make it be first in a polynomial ring. So I coerced the denominator into the ring, and that is the denominator. And then I can look at, remember that the Riemann hypothesis here tells you something at the factorization of these polynomials that are in the denominator and the numerator. So if I do factorization of the previous output, that's $1, we see that that is exactly what the Weil conjecture says about the zeta function. Fantastic. Can we actually see what's happening in the numerator? The numerator is supposed to factor, and the roots are supposed to have a certain norm, which is the root of 13, I think, in this case. So let's look at it also. So I'm going to call f is going to be the numerator this time of zeta. So what is f? That's the numerator now. And I can look at okay, number field of f. What is the number field now? That is, okay, so now I've defined a quadratic extension with that polynomial, and then I can look at, I'm going to change the rank of definition of the polynomial. So now it's defined over that quadratic extension. So I can look at the roots in the quadratic extension, see what those look like. That is the factorization. So it has 2 roots. And then I can actually pick those roots. Let's call it root is the roots, and then I can do the norm of root 1, and also look at the norm of root 2, 1, and see what happens. And there you go. That actually sort of depending on what the normalization is, depending on the normalization is of your Riemann hypothesis, the norm will be 13 or 1/13, or how we've normalized the polynomials. But if you work on it, you'll see that that is what the Riemann hypothesis says. So we've verified a huge theorem, the Riemann hypothesis for the zeta function. All right, fantastic. So let me go to what I like the most about magma is the functionality on elliptic curves. How can I call elliptic curves in magma? So elliptic curve, I can call it by, for example, its database name. So that is the Cremona label of that curve, the first curve in nature, the first elliptic curve in nature, they call this one. If you remember how the coefficients work, I can also call it by its coefficients. So I can call it by 0, -1, 1, 0, 0 will give me the same elliptic curve. Great. I can compute torsion subgroups. The torsion subgroup of an elliptic curve, or the torsion of the Mordell-Weil group, is quote unquote easy to compute thanks to a theorem of Nagel and Lutz that tell me that there are some very restrictive conditions on what points may be torsion points, and then there is an algorithm that is very efficient at computing torsion groups. And then you see that this elliptic curve in particular has some torsion. It has a point of order 5. If I remember, I can do up arrow for my last command. I'm going to call that T and ask magma, what is this group? And it insists that it's that abelian group. If I say, okay, what is the first generator of the group? It just tells me the first generator is the first generator. Because the torsion subgroup is stored right now in memory as an abelian group, as an abstract group. However, magma commands sometimes, as I think we saw before, they output two different things. So if I use a map, so it also outputs a map between the abelian group and actual points on the curve. So T1 will just give me an abstract generator, but if I send it to the elliptic curve, then it will give me the actual point that is the generator of a torsion subgroup. So I'm going to call that point P, and now I can do arithmetic on the elliptic curve with this point P. I can look at it with its 2P and 3P and 4P and 5P. And then you see that 0, 1, 0 is the origin. So we're back at the origin. So P has a order 5, right? Very good. And as before, let me know if you have questions. Brandon will stop me, and I can be interactive and do other things with you as we go along. Over Q, the torsion subgroups, a theorem of Mazur that was a conjecture of Levi that was reconjectured by Ogg and then later proved by Mazur in 77 or so, says that actually there is 15 types of torsion subgroups over Q. And once we know all those torsion subgroups, they can be cyclic or bicyclic, but there's only 15 types up to isomorphism. Once we know those, it turns out that over Q, every torsion subgroup, elliptic curves with a certain torsion subgroup, come in families, one parameter families with those torsion subgroups. And I can write down these families explicitly. But for example, I wanted to show you that I can write a family not just with a torsion subgroup, but families of elliptic curves with an isogeny, with a certain isogeny of a certain degree. So that family is actually given by this formula that I have here. So I'm going to just copy and paste it. So I'm just giving a random value t equals 7, and then I can define elliptic curve from a J invariant. So this is the J invariant family of elliptic curves with a 3 isogeny. So if I do this, I'm hoping I can see some isogenies. If I do isogenous curves to ET, there are 2 isogenous curves, probably itself, and then another one. And the 3, so I would put it, there are 2 things in the output, is the family of elliptic curves that are isogenous to it, itself, and another one. And these 3, at the end, it tells me that there is that the isogeny between them, or the maximum degree of a p-power isogeny, I believe, is 3. So the isogeny that I'm seeing there is 3. And if I change my number to something else, then I'm going to get another elliptic curve with a 3 isogeny, and it's just some different elliptic curves. Okay, very good. All right, so that's the torsion and isogenies. So let's go back to our elliptic curve E. That was 11A3 in Cremona, in the Cremona database, and let's look at the rank. So as we saw, I think in maybe the first lecture, the Mordell-Weil theorem tells me that the set of rational points, there is an abelian structure to it. I can put a group structure that has this nice geometric definition. And the Mordell-Weil theorem, or the Mordell theorem in the case of the rational numbers, tells me that this is a finally generated abelian group, and the rank of the free part of the Mordell-Weil group, that's what is called the rank, and or the rank of the if you take the rational points and do modulo torsion, then it is exactly isomorphic to copies of Z, and the rank of that module is the rank of the elliptic curve. In this case, the rank is 0, and you see that it says 0 true. That's because the algorithms that are behind computing a rank, they can be true in that it is provable that the rank is 0, or it might not say true, and it's just we cannot confirm it as at this point with these parameters. So what that means is that I'm going to have to work harder, or just be fine with just some rank bounds. I think I can also do rank bounds in E here, and that tells me that there are bounds that are provable, that the rank is at least 0 and at most 0, so it is true equals 0. All right. There are many questions that we don't know about the rank. We don't know if there are arbitrarily there are elliptic curves with arbitrarily high rank. The largest rank we know is 28, and it's an example by Elkis. It's not even provable that it's 28 unless you assume the Riemann hypothesis. So it is it's hard, but we know that the rank is at least 28 for that curve by Elkis. Another question that is interesting about ranks is what happens when I do quadratic twists of one elliptic curve. The quadratic twist, there's a different conjecture of what, or there's a different question of if, as I do quadratic twists, if the rank changes, if it can go arbitrarily high or not. And there is a lot of, there are a lot of different opinions about what can happen with ranks, but in the case we're seeing in terms of in the area of arithmetic statistics, we're seeing quite a bit of progress lately on understanding what's the distribution of ranks. However, we don't know yet, but let's look at quadratic twists. So I'm going to do a quadratic twist of my curve. Now I have to say I'm going to twist it by 2. And this is the quadratic twist. There is a formula you can find in Silverman's book, for example, or ask me later what's the formula of the quadratic twist. It just changes the coefficients slightly to get to another curve that is related. It has the same J invariant, but they are not isomorphic over Q. They're isomorphic in a quadratic extension, but not over Q. And then I can look at this elliptic curve and compute the rank of this elliptic curve. Is this has the rank changed? Yes, you see, I did a quadratic twist, so this is an elliptic curve with the same J invariant over Q. However, the rank now is 1 instead of 0, and it's also true, so it's that is provable. The rank is 1 in this case. Let's see if I can find an elliptic curve, a quadratic twist of this elliptic curve with a little bit higher rank. So what I'm going to do is copy here some code. I'm going to do a 4 cycle of quadratic twists and then print the rank on the screen and see what happens. Okay, so when I did quadratic twist 2 to 20, I get 1s and 0s. They're all provable, but there is no rank 2. All right, maybe we'll have to work a little harder. So let me copy and paste a little bit more code here. So now this code, what it did is that I defined what is the maximum rank you found, what is the winning twist, and then I'm doing a 4 cycle of quadratic twist, computing the rank, and then if the rank is larger than I had before, so I have a new record, then replace it and tell me what twist wins. So if I now do that, it turns out I found a quadratic twist of rank 2. I will have another additional problem in the homework today for you to see if you can find an elliptic curve of rank 0 and then see what is the highest rank you can find among quadratic twists. Some people think that this rank is bounded, that there is no quadratic twist, that there's some bound that you cannot go above with quadratic twists, or that, for each elliptic curve there is a bound, and as you move around quadratic twist, you get a bounded rank. But it's just, we don't know what the answer is, and there are opinions on both camps. All right, so, maybe we can see it. What is it? Is the quadratic twist of E by 58 has rank 2. Okay, so that elliptic curve is an elliptic curve of rank 2. Very good. And it started from an elliptic curve of rank 0. All right, let's look at an elliptic curve of rank 3. The most well-known elliptic curve of rank 3 is what the LMFDB calls the Gauss curve, because it was involved in the proof of, or finishing the Gauss class number problem for class number 1. So this was involved, this elliptic curve of rank 3 was involved in that proof. So now it's called the Gauss elliptic curve. I can look at the torsion subgroup of it. Let's see if I have a command here. This is torsion subgroup. It has no torsion, but the rank is 3 and true. So the methods that are behind magma can prove that the rank is 3. All right, I can figure out a little bit more information about my elliptic curve if I do Mordell, they. At this point, I can press tab and it will autocomplete to the only command that it starts with Mordell-Weiss is Mordell-Weiss information, and it tells me a little more information. Let me tell you what it outputs. It outputs the rank. So those are rank bounds. So this is now a little more detailed command. It outputs first how long it took to compute this. The computation took 0.047 seconds. And I computed the rank or CPU time, but I think it's seconds. The rank, the generators, and SHA, it was verbose, and it told me what is happening in the background. And then it computed the rank bounds, generators of the Mordell-Weiss group, and SHA, or generators of the entire Mordell-Weiss group, and SHA. SHA, that representation of SHA is, well, I'm not going to get into exactly what it's representing, but it's just saying that there is just no SHA. So SHA is trivial in this case, and it's computed. I guess I think it's the two part of SHA is trivial. That's what it is saying. The computation of SHA computed that that SHA has order 2. No, that SHA has order 2. That the 2 torsion of SHA is trivial. That's what it needed to compute the rank complete the rank computation. All right. So what is happening behind the curtains here in Magma is that it's using some method that is called the descent, the method of two descent. And what it does, and it is a very interesting topic that, well, it would take me too far afield to complete an explanation. But what it does is that it embeds the quotient of the torsion points modulo 2. So torsion points modulo twice torsion, rational points modulo twice rational points. It's embedded into something called a Selmer group that is computable. And this Selmer group, the elements of this group can actually be realized as other curves that are covering curves. So there are maps down to my elliptic curve. So these curves that are called homogeneous spaces where I have to try to find points on those and then see if there are points on my elliptic curve. The Selmer group is defined locally. So what I was actually doing is computing what kind of p-adic points and real points are there on these spaces, eliminating spaces where there are no points because there are local obstructions, and keeping those where there is no local obstructions. The spaces where there are no local obstructions and no rational points, or the spaces where there are no local obstructions but no rational points, those would be points that correspond to Shah elements. Spaces where there are no local obstructions and rational points, so where the global to local principle holds, those would be elements that are in the Selmer group that correspond to Mordell-Weil points. Okay, so in any case, it does this computation of the Selmer group and then tries to work out what elements of the Selmer group come from Mordell-Weil and what elements of the Selmer group come from Shah. And here it has realized that all the elements of the Selmer group come from the Mordell-Weil group, and it can complete the computation of the rank. Let me give you another example that is a little bit different, where there is some Shah. So E 571A1. Let's see what happens when I do my Mordell-Weil Shah information computation. So right now, it tells me that rank of E, the rank is 0. But how did it do this? So it is also saying that the analytic rank is 0, so it implies that the rank is 0. So here it's using something quite non-trivial, which is that we know parts of the Birch-Singleton-Dyer conjecture to prove that if the analytic rank is 0, then the rank is 0. Let's see what is actually happening also in a little bit more information. It's actually looking at a two-Selmer group. It's doing a two descent and seeing that Shah exists, that there is Shah elements in this case, and using the Cassel-Tate pairing, then is actually showing that the fourth torsion of Shah, there is no fourth torsion, is still two torsion. So it's computing the two primary component of Shah, and it's determined that it stops at two torsion. And then if it does, I believe it's doing a 4 descent, then it can complete the computation of the rank also algebraically without have to depend on some proof over the BSD for rank 0, for analytics rank 0 case. Okay, let's go back to the curve. To the Gauss curve. And what I'm going to do now is actually show you that in the LMFDB, if I go to my Gauss elliptic curve, then, well, I do have a lot of information. By the way, you see that the LMFDB gives me some different generators. There are the module that is Z3, there is many types of bases. So the one that Magma gave is not this one, but that's okay. And what I want is that the LMFDB, I hope you can see that, it spits out, it gives me all the code that they've used for, okay, I think Esteem wants to say something. All right. So the LMFDB tells me a lot of code that I can, if I don't know exactly how to do things, I can copy and paste this into my Magma window and find out a lot of, whoops, what happened? Oh no, Magma died somehow. Let me restart a window of Magma. Make the font bigger. Sure. Oops. Sorry about that. I don't know why Magma decided to crash. Let's. Why is that happening? Maybe there is some weird character that I'm copying down here. Let's copy. Let's just copy up to here and see what happens. This is what happens when you do things live. Let's see if this won't let me compute it. What? All right. Well, let's forget about that Magma code. This has worked before, so I don't know why right now it's giving me throwing a fit. But I've done that before and it was working fine. So I don't know what that's about. So let me just move on and say that, okay, let's go back to the elliptic curve. The Gauss elliptic curve. And what I wanted to do, actually, well, I wanted to look at a few things about the elliptic curve so I can compute a bunch of things such as, well, things that are actually related to the Birch and Swinnerton-Dyer conjecture. And what I wanted to do is verify the Birch and Swinnerton-Dyer conjecture that it holds for this one elliptic curve. So let's go back to, let's go back to the LMFDB and see that they are giving BSD invariants, but I want to show you is, again, what is the Birch and Swinnerton-Dyer conjecture. There's a nice explanation here of the Birch and Swinnerton-Dyer conjecture says, which is an conjectural analytic way, or I interpret this as a conjectural analytic way of computing the rank of an elliptic curve. So we don't know it in most cases. However, the conjecture says that the vanishing of the L function at s equals 1 equals the algebraic rank of the Mordell-Weil group. And then there is a formula. Once I take the rth derivative, that shouldn't vanish. And if I divide it by r factorial, then I get an exact formula for that residue at that point. So here is the formula that should happen. So let's try to compute things that we need for the Mordell-Weil group. And let's close this, minimize this one for now. And let's try to compute elements that we're going to need for the to verify BSD. First of all, let's see what the analytic rank of the elliptic curve is. So if I compute the analytic rank, what Magma is going to do is compute what is the analytic rank, what is the vanishing, and this is an approximation. So it's doing some numerical computation, and it's deciding that the vanishing is 3, which agrees with what we know, that the algebraic rank is 3, and then it outputs two things, and LR1 is the value that the Birch and Swinnerton-Dyer conjecture is telling me is important here. So it's taking the third derivative of the L function and evaluating at 1 and divided by 3 factorial in this case. So let's do that perhaps by hand. So I can also do that myself by computing the L series. So I can do like before I do zeta functions, I can compute the L series of E. So E, now L is an L function, and I can evaluate this L function whatever I want, but of course I'm interested in the value at 1. Now it's giving me a little bit more precision. The analytic rank command, it also had a precision set up, so I could have changed that. But anyway, this is the value at 1. It's 0, so it vanishes at 0. And then what I can keep is doing derivatives. So let's do the derivative. What derivative I want? Let's take first derivative of an evaluate. The derivative equals, oh, that's not how you write like that. So I take the first derivative, and it's something very close to 0, so it must be that it's almost 0. So let's assume that it's 0, and then let's see what happens with the second derivative. In this, there's a lot of computations going on in the background, so maybe for the third derivative, oh, let's time it, see how long it takes to compute the third derivative and evaluate it at 1. This is the value, and then it's 10.39. What I actually want is this value divided by 3 factorial, so I'm going to divide it by 6. Okay, and now it coincides with what analytic rank was telling me it was. So that value, I'm going to record it as BSD is this value. Okay. All right. Now let's look at the other side of the picture. So what is SHA? What is so I need to know what is the size of SHA. I need to know what is the real period, what is the regulator, what are the Tamagawa numbers, and what is the torsion. Maybe the easiest for now is to start with the torsion subgroup. We already did that. So let's compute again. Oops, wrong window. I'll come back to this one in a moment. Okay, so let's start with, remember the torsion subgroup is trivial, so tors is going to be just 1. The size of it is going to be 1. Let's look at the SHA. So I can compute the order of SHA from Mordell-Weil SHA information. So I can do rank gens SHA from Mordell-Weil information of E, Mordell-Weil SHA information, I think it is. It may be SHA info. Yeah. So now let's see what is the order of SHA. So I'm going to call order of SHA is 1. Very good. All right. Then I can, by the way, that is that the 2 torsion of SHA is trivial, but you can use some other tools to prove that. Well, in this case, I'm not sure to prove, but let's just assume that the rest of SHA is trivial, and I can compute the real period of E. There you go, omega. That is the real period. That is the second thing that appears in the formula. I can also look at what else do we need? We need the regulator. So the regulator is some volume of sort of heights of the of generators of the Mordell-Weil group. So what is the regulator? There it is. And Tamagawa numbers. 1. So the Tama is going to be 1. And now we're ready to prove, to verify the BSD conjecture. The BSD conjecture says that this number that we call BSD should be the same than the order of SHA times omega times, which is the real period, times, what do we have? The regulator times the Tamagawa numbers divided by the size of torsion, which I call it tors somewhere. Tors, the size of the torsion squared. Okay, so let's see. Oh no, we've disproved the Birch and Singleton-Dyer conjecture. What's happening? Why is this not agreeing? Well, you have to be very careful with one of these invariants. Well, first of all, maybe we made a mistake in the order of shot, but well, you can see how far are we from the answer. It's actually, you can multiply by 2 and get there. So if we were off by 2 and it was in SHA, we've already computed the 2 part of SHA, so that's not it. So what is the problem? The problem is with the real period. It turns out that the real period, I'm not sure is spelled out here. It turns out that if the connected component, if the real locus of the elliptic curve is disconnected, then I have to multiply by 2 what magma is saying. Okay, so let me see if I can go to, oh, there you go. I hope you see the graph of the curve is disconnected. So I actually have to fix my omega. Omega is actually twice this real period. And now I can compute that number and compute the BSD number, and they agree at least up to the last digit. Ta-da! Okay, so the BSD conjecture is verified up to a certain number of digits, so it's not a proof, and we have now completed how to verify one example of BSD, and in the exercises I'll tell you to I'll ask you to verify it in other cases. Okay. What else do I have? I don't have a lot of time left, so let me just show you. Maybe I'll explain why I had another window of magma running. So this is how you find points using magma on an elliptic curve, which is a genus 1 curve. But there are many times in research where some other higher genus varieties come into the picture, and then we're trying to find all the rational points on such varieties. So for example, here's one curve that Garen, who is in the audience, Garen Chiloyan, and I, working on a problem, we found this particular curve. So this curve, that it's too ugly to fit all in one place, but that curve over the rational field comes from a paper that we wrote together. So this paper on the classification of isogeny torsion graphs of elliptic curves, I'll send you a link to it. If you look at that paper in the archive, which has been submitted recently, what we're trying to do is classify all the isogeny graphs that happen over Q on elliptic curves. What kind of isogeny graphs are there? So you can see, by the way, Garen is giving a talk in the conference part. He was one of the speakers that will give one of the 20-minute lectures. And if you go to, let's see, where are we with the isogeny graphs? So these graphs that appear here are the possible isogeny graphs that can occur. Okay, so here's some tables with the graphs that can occur. And then at some point we had to prove that, for example, that these graph types, I hope you can see that, what we call an S-type, did not exist. To prove that, it turns out there are 2 different properties that need to be satisfied. And let me quickly go to the page where this is described. There are 2 different properties that need to be satisfied. One, we needed to know that two-adically there was a type of image, and that is described by one parameter family of elliptic curves, which is displayed on the screen. This comes out of a classification of Jeremy Rouse, who will be one of the speakers in the conference, and he will actually be talking about new work with David Drake Brown and I think Andrew Sutherland on three-adic images. And they've already classified what two-adic images can happen. So it has to be this two-adic image. And we have to have, the J invariant also has to have the property that has a 3 torsion, a 3 isogeny. So that is also given, as I did above in the magma code, is given by some other rational parameterization. So putting those together, that the J invariant has to have this shape, and that shape we get a curve, which is this curve that I have defined here. And the problem is that this curve has genus 13. And then the problem is, how do you do something with this curve? Well, you can read the paper. I think because I'm over time, I'm going to stop here. You can go to Garen's talk and see how we did it. But the key is that we realized that there were several simplifications one can do to bring it to do a map down to a genus 6 curve, then do a computation on the automorphism group of that curve, which is what Magma is trying to do here. So I defined the original curve, I simplified the model, and then from 13 to 6, and then I'm trying to compute the automorphism group. And this computation takes a long time. I put it to run again this morning, see if I could have it for this talk, but it's still running. Sometimes it takes a long time to do these computations. All right, so you compute the model of a quotient of this genus 6 curve by a quotient, and that gives you a map from a genus 6 curve to a genus 2 curve. And it turns out that this genus 2 curve, nowadays there is a lot of machinery implemented in Magma to take hyperelliptic curves, genus 2, and compute the points there. This works when something happens with what's the Jacobian variety, which you've seen in Soumya's class. You construct the Jacobian variety, and if the rank is smaller than 2, then you can use what's called the Chabot method to compute the points on that hyperelliptic curve. So that's what we did. We start 13, go down to 6, go down to 2, compute the points there, and then lift them up and see that there was nothing that was actually that made sense as an elliptic curve. There are cusps that you can throw down and up, and all the points that are on that 13 genus curve are just cusps. So they do not correspond to elliptic curves with the properties we were trying to rule out. So any case, as I said, go to Garen's talk, and you can learn more about that. And I think I'll stop here. So thank you for your attention, and enjoy using these algebra packages, because it's a lot of fun to do computations and to just get a feel for what these number theoretic objects are like. Thank you.